This evening, we are going to embark on a voyage throughout our entire solar system. But this will not be the typical tour you might be expecting. We are not merely going to discuss the planets and their moons. Instead, we are going to truly grasp the immense scale of our cosmic neighborhood. Because here is the reality that most people simply do not realize. When you look at diagrams of the solar system in school textbooks or on the internet, those images are actually lying to you. They are not doing it intentionally, but rather out of necessity. The actual distances we are dealing with are so incredibly vast that if you were to draw everything perfectly to scale, you would not be able to fit the image on a single page or a poster, or even on an entire football field. By the time we finish this journey, you are going to comprehend just how much empty space surrounds us. Before we get started, if you find these deep dives into space fascinating, dropping a quick like or subscribing would really help this channel grow. Let us start with what you believe you already know. You have likely seen countless illustrations of the solar system. You usually see 8 planets lined up in a neat row, perhaps with the asteroid belt sitting between Mars and Jupiter, and all of them circling a central star that appears to be roughly the same size as Jupiter. These pictures are useful for showing you what exists in our solar system, but they are completely wrong when it comes to scale. If those illustrations were accurate, if the planets were truly that close together relative to their physical sizes, everything would be different. Worlds would be constantly pulling on one another with their gravity. Catastrophic collisions would be common occurrences. The night sky viewed from Earth would be filled with the giant disks of our neighboring planets. But that is not what we see. When you look up at night, the planets look like bright stars. Even Venus, which is the brightest object and our closest neighbor, appears as nothing more than a point of light. There is a reason for that. The distances between these worlds are staggering when compared to their actual sizes. Let us put this into perspective with a simple example. If you had a basketball to represent our star, the Sun, and you placed it in the absolute center of a room, where do you think you would put Earth? Most people would guess somewhere in the same room, perhaps a few meters away. The real answer is that Earth would be a tiny ball about 2 millimeters across, roughly the size of a small bead, and you would have to place it about 26 meters or 85 feet away. That is the length of about 2 school buses parked end to end. And remember, that is just Earth, the 3rd planet. Neptune, the most distant planet, would be about 900 meters, or almost 3,000 feet, away. That is more than half a mile. You would need an entire football stadium to properly demonstrate this scale, and the vast majority of it would be nothing but empty air. Before we can fully appreciate the scale of the solar system, we need to start with something familiar. Let us start with Earth. Our planet measures about 12,742 kilometers, or 7,918 miles across. That seems quite large. If you wanted to walk around the equator, walking 8 hours a day at a steady pace, it would take you more than a year to complete the journey. If you drove non-stop at highway speeds, it would still take about 2 weeks. From our perspective down here on the surface, Earth feels enormous. There are oceans that stretch far beyond the horizon, mountains that take days to climb, and continents separated by thousands of kilometers of open water. You could spend your entire life traveling and still not see everything. But Earth is just one single planet. And when compared to some of the other objects in our solar system, it is actually quite small. The closest object to Earth, other than our artificial satellites, is the Moon. It circles us at an average distance of about 384,400 kilometers, or 238,855 miles. Let us make that distance more concrete. Light travels at about 300,000 kilometers, or 186,000 miles, per second. That means light from the moon takes about 1.3 seconds to reach Earth. When you look up at the moon, you are seeing it as it was just over a second ago. Astronauts who traveled to the moon during the Apollo missions between 1969 and 1972 took about 3 days to get there. The fastest spacecraft we have ever built, the New Horizons probe, would make that same trip in about 8 hours. Now, here is something truly interesting. If you wanted to line up all the planets between Earth and the moon, you could fit all 7 other worlds in our solar system inside that gap. Mercury, Venus, Mars, Jupiter, Saturn, Uranus, and Neptune, if you placed them side by side, would stretch about 390,000 kilometers, or 242,000 miles. That is just slightly more than the distance to the moon. Think about that for a moment. The space between Earth and our moon is wide enough to contain every single other planet lined up. That is how much nothing there is, even in this tiny corner of our cosmic neighborhood. Now, let us talk about our star, because understanding its size is crucial to grasping the scale of everything else. Our central star is staggering in size. It measures about 1,392,000 kilometers, or 865,000 miles across. That is about 109 times wider than Earth. If Earth were a grape, our star would be a sphere about 2.4 meters, or 8 feet, across. But diameter does not tell the whole story. Volume gives you a much better sense of the size difference. About 1.3 million Earths would fit inside the Sun. Imagine trying to fill it with Earths, like filling a jar with marbles. You would need 1,300,000 of them, and there would still be space left over. Our star also contains 99.86% of all the mass in the entire solar system. Everything else, all 8 planets, all the moons, all the asteroids, all the comets, all the dust, everything together makes up less than 0.2%. This central body dominates not just in size, but in mass. Every single second, it converts about 4 million tons of matter into energy through nuclear fusion. This energy radiates outward in all directions. The tiny fraction that hits Earth is enough to drive our weather, power photosynthesis in plants, and warm the surface to temperatures that allow liquid water to exist. The scale is so large that if you were standing on its surface and looking at the horizon, that horizon would be about 30 times farther away than Earth's horizon is from sea level. The surface area is about 12,000 times greater than Earth's. You could wrap our entire planet's surface around it 12,000 times and still not cover it completely. Now that we understand our star's size, let us look at the planets, starting with the inner solar system. This region contains 4 rocky worlds: Mercury, Venus, Earth, and Mars. These are called terrestrial planets because they have solid surfaces that you could theoretically stand on. Mercury circles closest to our central star at an average distance of about 58 million kilometers, or 36 million miles. We measure distances in the solar system using a unit called an astronomical unit, or AU. 1 astronomical unit is the average distance from Earth outward to the Sun, about 150 million kilometers, or 93 million miles. So Mercury travels at about 0.39 astronomical units. The smallest planet in our solar system, Mercury measures about 4,879 kilometers, or 3,032 miles across. That is about 38% the size of Earth. If Earth is a grape, Mercury is a large peppercorn. What is interesting about Mercury is how slowly it rotates. One day on Mercury, the time it takes to spin once on its axis, lasts about 58 Earth days, but it completes an orbit quickly, in about 88 Earth days. This creates a strange situation because it rotates slowly while traveling around our star relatively fast. One solar day on Mercury, from sunrise to sunrise, actually lasts about 176 Earth days. That is 2 Mercury years for every single day cycle. Mercury's surface temperature swings are extreme. During the day, temperatures can reach 430 degrees Celsius, or 806 degrees Fahrenheit. At night, they drop to minus 180 degrees Celsius, or minus 292 degrees Fahrenheit. That is a temperature swing of about 610 degrees Celsius, or 1,098 degrees Fahrenheit, more than any other planet. Venus travels next at about 0.72 astronomical units, or 108 million kilometers, which equals 67 million miles. Venus is almost identical in size to Earth, measuring about 12,104 kilometers, or 7,521 miles across. That is about 95% of Earth's width. Venus is often called Earth's twin because of the similar size, but the similarities end there. Venus has a thick atmosphere made of carbon dioxide that creates a runaway greenhouse effect. The surface temperature reaches about 470 degrees Celsius, or 878 degrees Fahrenheit, hot enough to melt lead. The atmospheric pressure at the surface is about 92 times greater than Earth's. If you stood on Venus, you would be crushed and cooked simultaneously. Venus also rotates backwards compared to most planets. While Earth rotates from west to east, Venus rotates from east to west. So sunrise happens in the west on Venus. Even stranger, Venus rotates very slowly. One day on Venus lasts about 243 Earth days. But Venus completes one orbit in about 225 Earth days. This means a day on Venus is actually longer than a year on Venus. Earth, as we have discussed, travels at 1 astronomical unit. We will come back to our planet later when we talk about what makes it special. Mars, the fourth world, circles at about 1.52 astronomical units, or 228 million kilometers, equal to 142 million miles. Mars measures about 6,792 kilometers, or 4,220 miles across, roughly half the size of Earth. Mars is sometimes called the red planet because iron oxide, basically rust, covers much of its surface. The average temperature sits at about minus 63 degrees Celsius, or minus 81 degrees Fahrenheit, much colder than Earth. One of the most impressive features on Mars is Olympus Mons, the largest volcano in the solar system. It stands about 21 kilometers, or 13 miles high, roughly 2.5 times the height of Mount Everest. The base of Olympus Mons spans about 600 kilometers, or 370 miles across. If you stood at the base, you could not see the summit because it would be beyond the horizon. Mars also has the largest canyon system we know. Valles Marineris stretches about 4,000 kilometers, or 2,500 miles long. If it were on Earth, it would span the entire United States from coast to coast. In places, this canyon is about 200 kilometers, or 125 miles wide, and up to 7 kilometers, or 4.3 miles deep. Between Mars and Jupiter lies the asteroid belt, a region filled with rocky objects. Despite what science fiction movies might show, this belt is mostly nothing. If you flew a spacecraft through it, you probably would not even see an asteroid with your own eyes. They are spread out over such a vast area that encounters are rare. The asteroid belt extends from about 2.2 astronomical units to about 3.2 astronomical units. That is a region about 150 million kilometers, or 93 million miles wide. Within this space, there are millions of asteroids, but most are quite small. The largest object here is Ceres, now classified as a dwarf planet. Ceres measures about 940 kilometers, or 584 miles across. Despite being the largest object in the belt, Ceres is much smaller than any of the 8 major planets. If you could somehow gather all the asteroids in the belt and combine them into one object, the total mass would be only about 4% of the Moon's mass. The entire asteroid belt contains less material than our Moon. This tells you something important. The asteroid belt is not the remains of a destroyed planet. It is actually material that never formed into a planet in the first place, probably because Jupiter's gravity disrupted the formation process billions of years ago. Now we come to Jupiter, and this is where the scale really starts to change. Jupiter circles at about 5.2 astronomical units, which is roughly 778 million kilometers, or 484 million miles. That is more than 5 times farther out than Earth. Jupiter is staggering. It measures about 139,820 kilometers, or 86,881 miles across. That is about 11 times wider than Earth. If Earth were a marble, Jupiter would be a basketball. But the real difference is in volume. Jupiter's interior is so vast that more than 1,300 Earths would fit inside with room to spare. Jupiter's mass is about 318 times that of Earth. Jupiter is so heavy that it contains more than twice the mass of all the other planets combined. Jupiter does not have a solid surface like Earth. It is a gas giant composed mostly of hydrogen and helium. If you tried to land on Jupiter, you would just keep sinking deeper and deeper into increasingly dense gas until the pressure would crush any spacecraft. Deep inside, there might be a rocky core, but we are not entirely sure. The Great Red Spot on Jupiter is a storm that has been raging for at least 400 years. Early astronomers spotted it through telescopes in the 1600s, and it is still there today. This storm is bigger than Earth. Our entire planet would fit inside the Great Red Spot with room around the edges. Wind speeds at the storm's edge reach about 432 kilometers per hour, or 268 miles per hour. Jupiter rotates incredibly fast for such a large planet. One day on Jupiter lasts only 9 hours and 56 minutes. This rapid rotation causes Jupiter to bulge at the equator. The planet is noticeably flatter at the poles than it is wide at the equator. Jupiter has at least 79 known moons, and scientists keep discovering more. The 4 largest moons, discovered by Galileo Galilei in 1610, are Io, Europa, Ganymede, and Callisto. Io is the most volcanically active body in the solar system. It has hundreds of active volcanoes constantly reshaping its surface. The volcanic activity is driven by tidal heating. Jupiter's gravity squeezes and stretches Io as it travels, generating heat through friction. Europa is one of the most exciting places in the solar system for the search for life. It has a smooth, icy surface, but scientists are confident there is a global ocean of liquid water beneath that ice. This subsurface ocean might contain twice as much water as all of Earth's oceans combined, kept liquid by tidal heating from Jupiter. Europa is smaller than our moon, but it might harbor more liquid water than our entire planet. Later missions found that Saturn's moon Enceladus also has a subsurface ocean with geysers shooting water into space. And scientists suspect several other moons, including Ganymede and Callisto, might have buried oceans as well. Ganymede is the largest moon in the solar system, even larger than the planet Mercury. It measures about 5,268 kilometers, or 3,273 miles across. Ganymede is the only moon known to have its own magnetic field. Callisto is heavily cratered, preserving a record of impacts from billions of years ago. These 4 moons alone make Jupiter like a miniature solar system. They are fascinating worlds in their own right, each deserving its own detailed study. Saturn travels at about 9.5 astronomical units, or 1.4 billion kilometers, which is 870 million miles. That is nearly twice as far out as Jupiter. Saturn measures about 116,460 kilometers, or 72,366 miles across. That is about 9.5 times wider than Earth. Saturn's volume is enormous, with space for about 760 Earths packed inside. Like Jupiter, Saturn is a gas giant composed mostly of hydrogen and helium. Saturn is actually the least dense planet in the solar system. If you could find a bathtub large enough, Saturn would float in the water. Saturn is famous for its spectacular ring system. These rings are made of billions of chunks of ice and rock, ranging in size from tiny grains to pieces as large as houses and even mountains. The rings extend hundreds of thousands of kilometers from the planet, but are surprisingly thin. In some places, the rings are only about 10 meters, or 33 feet thick. The main rings are divided into several sections. The A ring, B ring, and C ring are the most prominent. Between the A and B rings is a gap called the Cassini division, named after the astronomer Giovanni Cassini, who discovered it in 1675. This gap is about 4,700 kilometers, or 2,920 miles wide. Scientists are not entirely sure how old Saturn's rings are. They might be relatively young, perhaps only a few 100 million years old. The rings are gradually disappearing as ice particles slowly fall into Saturn's atmosphere. In a few 100 million years, Saturn might not have rings at all. Saturn itself has some remarkable features. At the North Pole, there is a hexagonal cloud pattern about 30,000 kilometers, or 18,640 miles across. This hexagon has been observed for decades, and scientists think it is created by a jet stream. But the exact mechanism that produces such a perfectly geometric shape is still mysterious. Saturn has at least 146 known moons, more than any other planet we know. The largest moon, Titan, is bigger than Mercury and measures about 5,150 kilometers, or 3,200 miles across. Titan is the only moon in the solar system with a thick atmosphere, denser than Earth's. The atmosphere is mostly nitrogen with some methane. Titan's surface has lakes and rivers, but they are not filled with water. They contain liquid methane and ethane. The temperature on Titan's surface is about -179 degrees Celsius, or -290 degrees Fahrenheit. Cold enough that methane exists as a liquid. Another fascinating moon is Enceladus, which is only about 500 kilometers, or 311 miles across. Despite its small size, Enceladus has geysers at its south pole that shoot water vapor and ice particles into space, fed by its subsurface ocean. The Cassini spacecraft flew through these plumes and detected organic molecules. Uranus circles at about 19.2 astronomical units, roughly 2.9 billion kilometers, or 1.8 billion miles out. At this distance, Uranus takes about 84 Earth years to complete one orbit. Uranus measures about 50,724 kilometers, or 518 miles across, about 4 times Earth's width. By volume, roughly 63 Earths would fill Uranus's interior. What makes Uranus unique is its extreme axial tilt. While most planets spin like tops, Uranus is tilted, on its side at about 98 degrees. Shutterstock. The planet essentially rolls along its orbit like a ball. This creates the most extreme seasons in the solar system. Each pole takes turns facing our star for about 42 Earth years at a time. During this period, one pole experiences continuous daylight, while the other is in complete darkness. Uranus is classified as an ice giant rather than a gas giant. It is composed mostly of water, methane, and ammonia in various states, with a relatively small rocky core. The methane in its atmosphere absorbs red light and reflects blue and green light, giving the planet its distinctive pale blue color. Uranus was the first planet discovered with a telescope. William Herschel discovered it in 1781. The discovery of Uranus instantly doubled the known size of the solar system. Uranus has 27 known moons and a faint ring system discovered in 1977. Neptune travels farthest at about 30 astronomical units, which is roughly 4.5 billion kilometers, or 2.8 billion miles out. At this distance, Neptune takes about 165 Earth years to complete one orbit. Neptune measures about 49,244 kilometers, or 30,599 miles across, slightly smaller than Uranus. Its interior volume holds about 58 Earths. Like Uranus, Neptune is an ice giant, but Neptune is more visually interesting because it has more dynamic weather. Neptune has the strongest winds in the solar system, with speeds reaching up to 2,100 kilometers per hour, or 1,300 miles per hour. That is faster than the speed of sound on Earth. Neptune's deep blue color is more vivid than Uranus's, because Neptune has more methane in its upper atmosphere. The planet also has visible features like the Great Dark Spot, a storm system observed by Voyager 2 in 1989. What is puzzling about Neptune is how it has such energetic weather despite being so far out. Neptune receives very little energy, about 900 times less than Earth does. Scientists think Neptune must have a strong internal heat source driving its atmospheric dynamics. Neptune was discovered in 1846 through mathematical predictions. Astronomers noticed that Uranus's orbit did not match predictions, calculated where another planet would need to be, pointed their telescopes at that location, and found Neptune. Neptune has 14 known moons. The largest, Triton, travels backwards, suggesting it was captured by Neptune's gravity. Triton is geologically active with nitrogen geysers and is slowly spiraling inward. In a few billion years, Neptune's gravity will tear Triton apart, possibly creating a magnificent ring system. Now that we have toured all 8 planets, let us step back. We have talked about sizes and distances, but it is hard to keep all these numbers in your head. Let us use a way to visualize this that really drives home how far apart everything is. Imagine you are driving across the United States from New York to Los Angeles, a distance of about 4,500 kilometers, or 2,800 miles. If our central star was sitting in New York's Times Square, where would the planets be along your route? Mercury would be in Philadelphia, about 140 kilometers, or 87 miles away. Venus would be somewhere around Pittsburgh, about 500 kilometers, or 300 miles from New York. Earth would be near Cleveland, Ohio, about 750 kilometers, or 465 miles away. Mars would be in Chicago, about 1,200 kilometers, or 745 miles from New York. Jupiter would be past Denver, about 2,500 kilometers, or 1,550 miles away. Saturn would be somewhere in Nevada, getting close to the west coast. Uranus would require you to continue past Los Angeles out into the Pacific Ocean. Neptune would be somewhere near Hawaii. This cross-country trip shows you how the distances scale up dramatically as you move outward. The inner solar system fits within the eastern half of the United States. But the outer solar system stretches thousands of kilometers beyond, and we have not even reached the edge yet. Here is what all these distances tell us. The solar system is dominated by nothing. If you randomly picked a point somewhere within Neptune's orbit, the overwhelming odds are you would find yourself in a void. Even the asteroid belt consists mostly of gaps between objects. If you were in a spacecraft traveling through it, you would probably have to intentionally navigate to see one up close. Objects are separated by hundreds of thousands of kilometers. This is hard for our brains to grasp because we live in a world full of things. Buildings, trees, cars, people, all packed relatively close together. But the solar system operates on a completely different scale. The distances are so immense that even light, traveling at 300,000 kilometers, or 186,000 miles per second, takes hours to cross. Let us think about the solar system in terms of light travel time, because this gives another perspective on the scale. Light from our central star takes about 8 minutes and 20 seconds to reach Earth. By the time you see that bright disk in the sky, you are seeing it as it was 8 minutes ago. Light takes about 43 minutes to reach Jupiter. It takes about 4 hours to reach Neptune. If our star suddenly vanished, we would not know about it for 8 minutes. For those 8 minutes, Earth would continue its orbit around nothing, receiving light that was already on its way. Then suddenly the light would cut off, and Earth would begin moving in a straight line. From our star to Mercury is about 3 minutes, to Venus about 6 minutes, to Mars about 12 minutes, to Saturn about 80 minutes, to Uranus about 2 hours and 40 minutes. These times might not sound that long until you remember that we are talking about light, the fastest thing in the universe. Nothing can travel faster. So these times represent the absolute minimum it would take for anything to travel between these locations. For human spacecraft, the times are much longer. The Voyager 1 spacecraft, launched in 1977, took about 40 years to reach the edge of the solar system and enter interstellar space. Both Voyager spacecraft are still traveling outward, moving at about 17 kilometers per second, or about 38,000 miles per hour. At this speed, they will not reach another star for tens of thousands of years. Let us talk about how long it would take to travel to different planets using current technology. The Apollo missions to the Moon took about 3 days each way. The Moon is about 384,000 kilometers, or 238,000 miles away. Mars is much farther. The distance between Earth and Mars varies depending on where both planets are in their orbits. At their closest approach, Mars is about 55 million kilometers, or 34 million miles from Earth. At their most distant, they are about 400 million kilometers, or 250 million miles apart. Spacecraft traveling to Mars typically take between 6 to 9 months. NASA's Perseverance rover, which landed in February of 2021, took about 7 months to get there. Jupiter is even farther. The Galileo spacecraft, launched in 1989, took 6 years to reach Jupiter. The Juno spacecraft, launched in 2011, took 5 years. Saturn is more distant still. The Cassini spacecraft, launched in 1997, took 7 years to reach Saturn, arriving in 2004. No spacecraft has ever been specifically sent to Uranus or Neptune. The only close-up observations we have come from Voyager 2, which flew past Uranus in 1986, and Neptune in 1989. Voyager 2 launched in 1977. So it took 9 years to reach Uranus and 12 years to reach Neptune. Let us think about speed for a moment, because understanding speed helps us appreciate the distances involved. The fastest manned vehicle ever built was the Apollo 10 command module during its return from the Moon in May of 1969. It reached a speed of about 39,900 kilometers per hour, or about 24,791 miles per hour. At that speed, you could travel from New York to Los Angeles in about 6 minutes. But even at that incredible speed, it would take about 43 days to reach our star, about 4 years to reach Jupiter, about 8 years to reach Saturn, and about 17 years to reach Neptune. The fastest unmanned spacecraft we have built is the Parker Solar Probe, launched in 2018. At its fastest, the Parker Solar Probe reaches speeds of about 690,000 kilometers per hour, or 429,000 miles per hour. At that speed, it could travel from New York to Los Angeles in about 7 seconds. Even at this incredible speed, it would still take about 2.5 days to reach our central star, about 2 months to reach Jupiter, about 4 months to reach Saturn, and about 9 months to reach Neptune. These numbers show you that even with our best technology, the solar system is staggering in size. The distances between planets are so large that journeys take months or years. We have talked about the 8 planets, but the solar system does not end at Neptune. Beyond Neptune lies the Kuiper Belt, a region filled with icy bodies left over from formation billions of years ago. The Kuiper Belt extends from about 30 astronomical units to about 50 astronomical units. In comparison, Neptune travels at 30 astronomical units. So the Kuiper Belt begins right at Neptune's orbit and extends outward for another 150 million kilometers, or 93 million miles. The Kuiper Belt contains thousands of known objects and probably hundreds of thousands more waiting to be discovered. Most are small, just a few kilometers across, but some are quite large. Pluto is the most famous Kuiper Belt object. Pluto circles at an average distance of about 39.5 astronomical units, which is roughly 5.9 billion kilometers, or 3.7 billion miles. Pluto takes about 248 Earth years to complete one orbit. Pluto measures about 2,377 kilometers, or 1,477 miles across, smaller than Earth's moon. When Pluto was discovered in 1930 by Clyde Tombaugh, it was classified as the 9th planet. It held that designation for 76 years. But in 2006, the International Astronomical Union redefined what makes a planet. Under the new definition, Pluto did not qualify because it has not cleared its orbit of other debris. Pluto was reclassified as a dwarf planet. This decision upset many people who had grown up learning about 9 planets. But the reclassification made sense scientifically. Once astronomers started discovering other objects similar to Pluto in the outer solar system, they faced a choice. Either include all these objects as planets, which would mean adding dozens or even hundreds, or create a new category. They chose the latter. The New Horizons spacecraft flew past Pluto in July of 2015, giving us our first close-up look. The images revealed a complex and geologically active world that surprised scientists. Pluto has mountains made of water ice that reach 3,500 meters, or 11,500 feet high. There are plains of frozen nitrogen that appear to be geologically young. There is even evidence of possible ice volcanoes, called cryovolcanoes. The most famous feature on Pluto is a large heart-shaped region called Tombaugh Regio. The left side of this heart is a smooth plain of nitrogen ice called Sputnik Planitia. This plain shows patterns that suggest convection, where warmer ice rises and cooler ice sinks, similar to how a pot of boiling water circulates. This suggests Pluto has internal heat that keeps the nitrogen ice soft enough to flow. Pluto has 5 known moons. The largest, Charon, is about half Pluto's width. That is unusual. Most moons are much smaller than their parent planets. Charon is so large relative to Pluto that some scientists consider them a binary system, 2 objects circling a common point in space between them. Charon itself is an interesting world. It has a dark reddish pole, probably caused by methane from Pluto's atmosphere that freezes onto Charon's surface and is then chemically altered by solar radiation. Charon also has fewer craters than expected, suggesting it might have been geologically active in the past with internal processes that resurfaced parts of the moon. Pluto's other 4 moons, Styx, Nix, Kerberos, and Hydra, are much smaller and irregularly shaped. They are probably captured Kuiper Belt objects or fragments from an ancient collision. Other significant Kuiper Belt objects include Eris, Makemake, and Haumea. Eris is slightly smaller than Pluto, but more massive. It travels at about 68 astronomical units on average, though its orbit is highly elliptical, taking it as far as 98 astronomical units at its most distant point. Eris takes about 557 Earth years to complete one orbit. The discovery of Eris in 2005 was actually the main trigger for Pluto's reclassification. When astronomers found an object farther out and more massive than Pluto, they had to decide, is this the 10th planet, or do we need to rethink what we call a planet? The decision to reclassify Pluto came the following year. Eris has 1 known moon, Dysnomia, which is much smaller than Eris itself. By watching Dysnomia's orbit, scientists calculated Eris's mass and found it to be about 27% more massive than Pluto, even though it is slightly smaller in width. This means Eris is denser than Pluto, probably containing more rock and less ice. Makemake is slightly smaller than Pluto and travels at about 45.8 astronomical units. It takes about 306 Earth years to complete one orbit. Makemake's surface is covered with frozen methane, which gives it a reddish color. It has 1 known moon discovered in 2016, which scientists creatively named MK2. Haumea is particularly interesting because it is shaped like an egg rather than a sphere. It rotates very rapidly, completing one rotation in less than 4 hours. This rapid spin stretches Haumea into an elongated shape. The best measurements suggest Haumea is about 2,300 kilometers, or 1,430 miles long, but only about 1,700 kilometers, or 1,056 miles wide. What caused Haumea to spin so fast? Scientists think it might have been involved in a massive collision billions of years ago. The impact would have sent Haumea spinning and might have created the 2 known moons and a family of smaller objects that share similar orbits. Haumea also has rings, making it one of only 5 objects in the solar system known to have rings. The others are the 4 giant planets: Jupiter, Saturn, Uranus, and Neptune. Haumea's rings were discovered in 2017 when astronomers watched Haumea pass in front of a distant star. The star's light dimmed briefly before and after Haumea blocked it, revealing the presence of a ring. Beyond the Kuiper Belt, at truly staggering distances, lies the Oort Cloud. Getty Images. This is a theoretical shell of icy objects that surrounds the entire solar system like a bubble. The Oort Cloud is thought to begin at about 2,000 astronomical units, and extend as far as 100,000 astronomical units. To put that in perspective, 100,000 astronomical units is about 1.6 light-years. That is about 1/3 of the distance to the nearest star. We say the Oort cloud is theoretical because we have never actually observed it directly. It is too far away, and the objects are too small and too dark to see with current telescopes. But we infer its existence from the comets we see. Long-period comets, comets that take hundreds or thousands of years to complete their orbits, are thought to originate from the Oort cloud. Sometimes, gravitational disturbances from passing stars or giant molecular clouds nudge these icy bodies, sending them falling towards the inner solar system. The famous Halley's Comet, which appears in Earth's sky about every 76 years, is thought to have originated from the Oort cloud before something perturbed its orbit into a shorter period. The last time Halley's Comet was visible from Earth was in 1986. It will return again in 2061. If the Oort cloud extends to 100,000 astronomical units, then that is the true boundary of the solar system. That is where our star's gravitational influence effectively ends. Beyond that, objects are more influenced by the gravity of other stars. The Oort cloud might contain trillions of objects. Some estimates suggest there could be 2 trillion or more icy bodies larger than 1 kilometer across in the Oort cloud. But they are spread across such an enormous volume that they are effectively invisible to us. The density of objects in the Oort cloud is incredibly low. If you were standing on one Oort cloud object, you probably would not be able to see any others with the naked eye. They would be too far away and too dark. The structure of the Oort cloud is thought to have 2 parts. The inner Oort cloud, also called the Hills cloud, is a disc-shaped region. The outer Oort cloud is more spherical, surrounding the entire solar system in all directions. This spherical distribution means that comets from the Oort cloud can approach from any angle, not just from the plane of the planet's orbits. Understanding the Oort cloud helps us understand the solar system's formation and evolution. The objects in the Oort cloud are thought to have originally formed much closer, in the region where the giant planets now travel. During the early solar system's chaotic period, when the giant planets were migrating, they scattered many objects outward. Some were ejected entirely. Others ended up in the Oort cloud, where they have remained for billions of years. The Oort cloud is also vulnerable to outside influences. When other stars pass relatively close to the solar system, their gravity can disturb the Oort cloud, sending showers of comets into the inner solar system. This might explain periods of increased comet activity in Earth's history. Let us talk about how planets actually move through space, because understanding orbital mechanics helps us appreciate the scale. All the planets circle our central star in roughly the same plane called the ecliptic. If you imagine the solar system as a disk, all the planetary orbits lie close to this disk. This is not a coincidence. It is a result of how the solar system formed from a rotating disk of gas and dust. But the orbits are not perfect circles. They are ellipses, or oval shapes. Some orbits are nearly circular, like Venus and Neptune. Others are more elongated, like Mercury and Pluto. An elliptical orbit means the planet's distance changes as it travels. When the planet is closest, it is at perihelion. When it is farthest, it is at aphelion. Earth's orbit is nearly circular, so the difference between perihelion and aphelion is only about 3%. But for Mercury, the difference is about 24%. This affects how fast planets move in their orbits. When a planet is closer, it moves faster. When it is farther away, it moves slower. This is described by Kepler's second law, which states that a line from our central star to a planet sweeps out equal areas in equal times. In simpler terms, a planet speeds up when it gets closer and slows down when it gets farther away. The closer a planet is to our central star, the faster it travels. Overall, Mercury zips around in just 88 Earth days. Neptune takes about 165 Earth years. This relationship between distance and orbital period is described by Kepler's third law. There is also the issue of orbital inclination, how tilted a planet's orbit is compared to Earth's orbital plane. Most planets have orbits that are fairly close to the same plane. Mercury has the highest inclination among the planets at about 7 degrees. Pluto, for comparison, has an inclination of about 17 degrees, which is one reason it was reclassified as a dwarf planet rather than a full planet. Understanding these orbital mechanics is crucial for space missions. When we send a spacecraft to another planet, we cannot just point it at the planet and fly straight there. The planet will have moved by the time the spacecraft arrives. Instead, mission planners use what are called Hohmann transfer orbits, which are basically the most fuel-efficient curved paths between two orbits. A Hohmann transfer orbit is like throwing a ball to someone who is moving. You do not throw it at where they are now. You throw it at where they will be when the ball gets there. This means spacecraft can only launch to certain planets during specific launch windows, when the planets are in the right positions. These launch windows occur at regular intervals. For Mars, launch windows occur about every 26 months. For Jupiter, they occur about every 13 months. Missing a launch window means waiting for the next one. This is why space missions are planned years in advance. To really understand the scale of the solar system, it helps to know how it formed. Because the structure we see today, with small rocky planets close in and giant planets farther out, is a result of processes that happened 4.6 billion years ago. The solar system formed from a giant cloud of gas and dust called the solar nebula. This cloud was about 2 light-years across and contained all the material that would eventually become our star, the planets, and everything else. Something triggered the collapse of this cloud. It might have been a shock wave from a nearby supernova, the explosion of a massive star. The shock wave compressed the cloud, and gravity did the rest. As the cloud collapsed, it began to spin faster like a figure skater pulling in their arms. The spinning caused the cloud to flatten into a disk with a bulge at the center. Most of the material fell toward the center, where it became increasingly dense and hot. Eventually, the center became hot and dense enough for nuclear fusion to begin, and our star was born. But not all the material fell into our central star. The material in the disk began to clump together through a process called accretion, which just means particles sticking together. Tiny particles of dust collided and stuck together, forming larger and larger objects. These grew from dust grains to pebbles to boulders to small planets called planetesimals, basically baby planets. The planetesimals continued to collide and merge. In the inner solar system, where temperatures were high, only materials that could withstand heat remained solid. These were mostly metals like iron and nickel, and rocky materials called silicates. The lighter, more volatile materials, things like water and methane that turned to gas easily, were vaporized by the heat. This is why the inner planets are small and rocky. In the outer solar system, beyond what is called the frost line, temperatures were cold enough for volatile materials to condense into ice. This meant there was much more solid material available for planet building. The cores of Jupiter, Saturn, Uranus, and Neptune grew large enough that their gravity began attracting the abundant hydrogen and helium gas. Jupiter and Saturn accumulated enormous atmospheres, becoming gas giants. Uranus and Neptune, being farther out where the nebula was less dense, accumulated less gas and more ice, becoming ice giants. This entire process took about 100 million years. By about 4.6 billion years ago, the basic structure was in place. But the solar system was not done changing. For the next few 100 million years, the planet's orbits were not stable. Gravitational interactions caused the giant planets to migrate, moving inward or outward from their original positions. Jupiter probably migrated inward toward our central star, then back outward. Saturn, Uranus, and Neptune migrated outward. This migration had dramatic effects. As the giant planets moved, they scattered smaller objects throughout the solar system. Some were thrown inward. Some were ejected from the solar system entirely. Some were thrown into the inner solar system, where they bombarded the young terrestrial planets. This period of heavy bombardment lasted until about 3.8 billion years ago. During this time, the inner planets, including Earth, were constantly struck by asteroids and comets. These impacts brought water and organic compounds to Earth, which might have been crucial for the origin of life. The migration of the giant planets also explains some puzzling features of the solar system. The Kuiper belt structure, with certain regions nearly devoid of objects and others more densely populated, is thought to be a result of Neptune's outward migration.